today to introduce Max Trostel's comps, predicting the weather, the physics of Earth's atmosphere. He's presenting on something that's been interesting to him since even before high school, and that is especially topical considering our recent weather. Besides being a great physicist, he's also a cheerful and helpful presence who's great to have around the physics department. So please join me in welcoming Max.
Thank you so much, Anne, for that wonderful introduction. I'm just going to get started in 1 second here. So, like Anne mentioned, I've been interested in the weather since I was a little kid, and it's been really enjoyable over the last couple of months to learn about the physics behind how the weather happens, and also to learn how we can predict the weather using physics. So I think it would be inappropriate to not mention the week of weather that we've had. It's been one of the coldest weeks throughout the Midwest in a couple decades in some places. Here's just a plot of the temperature in blue and wind chill in yellow over the last 72 hours, ending sometime last night. And you can see it was below zero for about 72 hours. And at one point, it got below 30 below for the temperature, and even to minus 54 or so for the wind chill here in Northfield. So pretty impressive. And that sort of brings me to the motivation for my talk, which is, so why should we predict the weather? And I think in this day and age, it's kind of hard to even imagine what it would be like without a weather forecast. And certainly this is even more important for businesses who rely on weather forecasts, anything from transportation to logistics, insurance, farming, preparations for storms. There are all these things that we rely on today that rely on weather forecasts. So with that, I'm going to get right into what I'm talking about today. So I'll do a little introduction to what weather prediction is and the problem that we're facing in trying to predict the weather. And then I will spend the bulk of my talk on the equations of the atmosphere, which is really where the physics, the fundamental physics of the atmosphere comes in. And then I'll spend a little bit of time on the Coriolis effect and clouds and precipitation. So to start off, what is the weather? Now this might seem like a pretty easy question to answer, but we want to make this specific and quantitative. So how are we going to measure the weather? There are 4 state variables that we use to talk about the weather at a particular point in space and time. These are temperature, humidity, pressure, and density. I will be referring to them a lot throughout this talk, so I've written them on the board here below. Hopefully you can all read those. And of course, those describe the state of the air, but we also need to know how it's moving, and that's where the wind speed and direction come in. So you're probably familiar with a lot of these quantities except for maybe density, because these are sort of things you might measure at your house. Okay, so with that, one thing we're missing is clouds and precipitation, which is certainly an important aspect of the weather, but not something that we are actually measuring in the air, but more something that exists around the air. So when we talk about the weather happening, of course it's in the atmosphere, but really it's in this bottom layer of the atmosphere called the troposphere. And this is the bottom about 10 to 20 kilometers. It's closer to 10 kilometers in width near the poles, and thicker near 20 kilometers near the equator because of the effect of heating from the sun. And this is basically where all the weather happens, because there's this decreasing temperature gradient as you get higher and higher in elevation. And then that stops at what's called the tropopause, which basically caps weather, and it caps the clouds so that they can't go any higher than that. And the atmosphere in the troposphere is made mostly of nitrogen and oxygen, a little bit of other stuff. But one of the more interesting quantities that varies is the concentration of water vapor. And so this takes up about 0 to 5% of the mass of the atmosphere at a given point. So how are we going to go about predicting the weather? Well, for a long time, people have been trying to predict the weather with sort of rules of thumb. You might have heard the old saying, red sky at night, sailor's delight, red sky at morning, sailor's warning. And these are sort of sayings that were based on what people experienced with the weather, and they actually do have some merit in being able to forecast what the next day or two might look like. But they're obviously very imprecise techniques, and they're only useful for maybe a day or two. And we can get a little bit more advanced with this type of forecasting by really measuring the atmosphere at different points really well. And so we can set up weather stations, and we can set up a communication network between different parts of countries and different countries so that they can talk about what the weather is where they are and where it's moving. And that can kind of help get an idea of what's going on. And this was the method that they used to produce forecasts during World War II, which was certainly an important part of trying to fight that war. And here are some World War II meteorologists working on a forecast based on these sort of rules of thumb. Now, weather prediction as we know it really got started when computing came along, because we can effectively reduce the problem of predicting the weather into small arithmetic computations that computers can do. And the first computer to do this was the ENIAC computer at UPenn. That stands for Electronic Numerical Integrator and Computer. And this was one of the very first Turing-complete computers in the world, and is thought to be the first computer that was general-purpose programmable computer. And immediately when they were building computers, a lot of scientists were thinking, okay, how can we use this to predict the weather? And sure enough, it didn't take them long. They got started on this, and by 1950, they had produced the first successful weather forecast. And some really high-profile people working on this, a lot of you might recognize the name John von Neumann, extremely famous mathematician who also did some physics. And he was involved in this weather forecast, which shows how important it was to get this going at the time. And what was amazing about this forecast is that they managed to produce a 24-hour forecast with the simplified equations in less than 24 hours. It was only slightly less than 24 hours, so it was basically useless, but it demonstrated that, okay, as the computing power increases, we should be able to actually make weather forecasts that are useful. And the second thing that came along that was important in developing weather forecasting was weather satellites. This allowed humans for the first time to really observe the entire atmosphere in some way. And the combination of computing and weather satellite technology basically allowed for steady improvements in our ability to forecast the weather over the last 50 years. So what do we really mean when we're talking about producing a forecast with computers? So this goes into something that's called numerical weather prediction, which is what we essentially use to forecast the weather today. And the way this works is by turning weather prediction into a calculus problem. Using physics, we can come up with equations and initial and boundary conditions, and a lot of you are familiar with doing initial value problems and boundary value problems for math classes and physics classes, and we can basically reduce the weather with some simplifying assumptions into this type of a problem. And then the computers come in and we can use them to integrate them as finite difference or finite element problem. So that should give you some idea of where weather prediction has come from. And now we're going to get into the part where the physics happens, which is in the equations that these computer models use. So over here, you can see we have these 5 variables we're using to describe the atmosphere at different points in space and time. Now, this means we basically have a problem with 5 unknowns. Some might say 7 because velocity really has 3 components, but we're going to call it 5. So this means in order to determine the system, we will need 5 equations. And it turns out that the equations we'll use are 4 partial differential equations and 1 algebraic equation. And this is where the physics happens. Okay, so here are the equations. Don't look at them too hard. They look kind of scary. So So those might look really complicated, but I can promise you that they actually come from really simple ideas in physics that many of you are familiar with. And these principles are the idea of an equation of state, conservation of mass, both for the total mass and for the mass of water vapor in the system, and also conservation of energy and momentum. So certainly the physics majors will be familiar with all of these ideas. So how do we get these sort of complicated looking equations from these really basic ideas. So let's start with the first equation, the equation of state. This is the one algebraic equation, which is not a differential equation, so it's kind of a simple place to start. Generally, we can define an equation of state by one that relates pressure, temperature, density, and composition. So we can write pressure as a function of those three variables. And in the case of the atmosphere, we're writing our equation of state as this, where you can see we've got our density and temperature and pressure, and we've also got Q, which represents the humidity, or the concentration of water in the air by mass. The other quantity that you can see in there is the specific gas constant for dry air. This equation might look unfamiliar to you, but really it comes from the ideal gas law, which many of you have seen before. And if we scoot things around and put things in terms of density rather than volume, and make a change from the true gas constant to this specific gas constant, which depends on the molar mass, and then we rewrite the specific gas constant as a function of Q, which is basically what we're doing here. You can derive this quantity, but we won't do that today. So we got this equation. In order to form some intuition behind this, I played around with some vet sims from the University of Colorado, and you can see if we put more mass into the system, in other words, increase the density, then the pressure is going to go up. It went up from about 1.4 to 1.9. We can show that again. So it starts around 1.4. We pump some more molecules into this box, and the pressure goes up. Right? This makes sense. You put more objects into a confined space, they're hitting each other more, and they're going to exert more pressure. The other variable we'll look at is temperature. So if we heat this up, we increase the temperature, the pressure also increases with that. So it makes sense that in our equation of state, the pressure is going to increase linearly with both density and temperature. It's a little harder to explain how the water vapor part comes in, but you can sort of imagine it relating to Avogadro's law that equal volumes with the same pressure and temperature have the same number of molecules, which means that since water vapor, H2O, is lighter molecularly than N2 or O2, nitrogen and oxygen, that means that it will exert more pressure at a given density and temperature for the same number of molecules, or for a greater number of molecules because the density is increased. And this has a really important implication in the atmosphere that you've maybe heard of before, which is that moist air rises. So when air is saturated with water, let's say it's over the ocean and water comes into the air, it will rise up. And this you can see directly follows from this equation of state. So we've talked about our equation of state. Now, before we talk about the rest of the equations, I'm going to discuss something I sort of snuck past you, which is why are all of these capital D derivatives for? What does that mean? If you've taken calculus, you've certainly seen derivatives, but why with the capital D? Well, what this derivative is the material derivative, which I've written out here also for reference. And you can derive that from the chain rule for multiple dimensions. And you basically get that we can write this material derivative in terms of the partial derivative of the quantity with respect to time plus the velocity dotted with the gradient of the quantity. And so, for those of you who aren't super, or sorry, never mind. So, how does, basically these two different derivatives are telling you about different rates of change. This first derivative is how F is changed, this quantity F, some quantity in a field, is changing with following a particle in a fluid, while the partial derivative is presuming it's at a fixed location, right? Because all of these quantities are defined also in space, so we have to consider, okay, how does space change? And to make this a little bit more intuitive, so we're not lost in all the math, we can imagine that the partial derivative, let's say we're measuring temperature at this particular point in a fluid that's flowing around this airfoil. So when we talk about the partial derivative, we're saying, okay, how is the temperature of this fluid changing at that spot, right there? Whereas when we're talking about the material derivative, it's like we're following along with the fluid, following a particular particle in the fluid, and now we're talking about how the temperature is changing. And so these are two very different quantities, but they're both that are useful in atmospheric science, because the material derivative is what we'll use when we're talking about how is physics acting on a particle in the fluid, whereas the partial derivative we'll use when we're talking about, okay, how is the quantity changing at a specific point in space, such as at a weather station? Okay, so now that we've got that out of the way, we can start talking about the rest of our equations. The first equation we have is, the first differential equation we have is the conservation of mass equation, which we write here. We can get some intuition behind what this equation means by thinking about the divergence of the fluid, which is this quantity del dot F. And to get an idea of what the divergence means, we can sort of consider what, whether it's positive or negative and how that affects the flow of fluid. So if our divergence of the velocity field is negative, that means basically the opposite of divergence, it's converging. Whereas in the case where the divergence is positive, we have our velocity vectors all pointing away from each other, and so the particles are spreading out. And in the case where it's zero, we have a fluid moving, but the particles aren't changing distances from each other. And we can see this a little bit better with these animations I'm borrowing from 3 Blue 1 Brown. It makes really great animations. And we can see when it's negative, velocity field vectors are pointing inwards, and so the particles follow their velocities and they become more dense. And you can see the opposite happens in the case that the divergence is positive. And then for a fluid which has zero divergence, our particles are moving around according to a velocity field where they're not getting closer or further away from each other. So getting back to this equation, we can now interpret what this means. Basically, it's telling us that the rate of change of the density will be equal to the opposite of the divergence of the fluid times the density already. And so that means that when the density increases, fluid is coming together so that divergence is negative, and it'll happen faster if the fluid is already more dense. Okay. So we have another one of these conservation of mass equations, which is just for water vapor. And I won't talk about this in depth because it's one of the equations which is dependent on what we call a parameterized function, which basically means we can't model this dynamically with fundamental physics, and instead we have to make empirical observations about how water vapor flows into and out of clouds, raindrops, from the surface when it evaporates over the ocean, when it condenses on land. And so in order to take into account all of those things, we have what we call a parameterized function, which is based on empirical evidence. So we won't go into that more other than to just say that the rate of change of the humidity will just be equal to the flow of water vapor into and out of a section of air. So moving on to conservation of energy, we write the conservation of energy equation for the atmosphere as such. And this might look totally unfamiliar to you, but it's completely analogous to the first law of thermodynamics, which is that the change in the internal energy of the system is equal to the heat that flows into the system plus the work that's done on the system. And because the work that's happening in the atmosphere is compressive work, we can write that as the change in the pressure with respect to time, and we write Q as the heat flux, which means that it's the rate of change of heat, it's the heat flow per time per unit mass. And then the quantity on the left is also a rate of change of temperature, which is proportional to energy, the internal energy of the system, of course. So this kind of shows how conservation of energy follows directly from the first law of thermodynamics. Finally, we have made it to conservation of momentum. And this is the equation that has the most terms, but really we can just focus on this very first term because this is the fundamental physics part for the fluid. And so we can imagine that if we just look at this part of the equation, that's the equation for a massless, non-rotating Earth with no fluid viscosity, right? And so these other terms are the gravitational fields with an asterisk because there's also some rotating frame effects in there, the Coriolis effect, and then the friction, which comes out of the viscosity of the fluid. But focusing just on this beginning part, we can see that it contains what's called the gradient of a function. And so we can visualize this gradient through its definition by considering that the gradient points in the direction up the slope, and its magnitude is equal to how steep the slope is at that point. So you can see for this 2D, spatially 2D defined function, its height is this quantity pressure P, and we can see that the vectors here below, which are the gradient, point in the direction of upward slope, and they point with a magnitude equal to the steepness. And so when we think about what this equation means for the atmosphere, you can see that the flow is going to accelerate opposite the direction of the gradient. And this makes sense for the atmosphere. You might have heard that wind blows from a high pressure to a low pressure. And this makes a lot of sense because if you imagine we have a box here where there are more particles in the left, so it's a higher pressure fluid, and fewer particles on the right, so it's a lower pressure fluid. And then we take away this divider, and more blue particles are going to flow right, which basically means that there's a net acceleration of fluid towards the right. Okay, so we've ignored the gravity and the mass of the Earth, and we've also ignored the fact that it's rotating. So it's almost as like we're living on a flat, massless Earth. But of course, the Earth is not flat. And it's also not inertial because it's rotating. It's really a spinning sphere, or to be more precise, it's a spinning oblate spheroid, which just means it's a slightly squished. Okay, so this brings us to the next section of my talk, which is on the Coriolis effect, which comes out of the fact that the Earth is a sphere and it's rotating. Okay, so we see the Coriolis acceleration is a part of our conservation of momentum equation, but where does this term come from? Well, it comes from the fact that Newton's laws are only valid in inertial reference frames. We can write this down with the first law just by stating that if the net force on an object is 0, then the acceleration of that object should be 0. Which maybe seems sort of circular to you because we've just defined what Newton's laws are in terms of an inertial frame and the opposite as well. But really they're equivalent, they're definitions. Newton's laws are valid in an inertial frame. An inertial frame is a frame in which Newton's laws are valid. So anyway, the Earth is not one of these inertial frames, but we can pretend that it is in this room because it's rotating pretty slowly and we're taking up just a really tiny, small part of it. Okay, so in order to get into this, how are we going to determine what the apparent forces are on a body in a rotating reference frame? Because this is important on Earth because here we are, we're fixed on the surface of the Earth, and it feels like we're not rotating, but we really are. And so how does this affect the forces on the fluid of the atmosphere? Well, we can write out what we are trying to find with this idea that the apparent force is equal to the true force on an object plus these fictitious forces. And so in order to derive what these fictitious forces, these forces that seem to be acting on objects even though they don't really exist, we need to compare accelerations for the same object in two different frames, one in an inertial frame and one in a rotating frame. So to start off to find these two different accelerations and how they relate to each other, let's set up this problem. So imagine a point P with position vector r. You can also see it here on my rotating table here, where the rubber ducky is the point P, this is the vector that's r, and our coordinate system, x, y, z, is lying on it, just like that. And we can imagine that we can start rotating this inertial frame, and the vector r will be constantly changing in time because it's rotating around. Okay, so that means that in an inertial frame, which we could pretend the room is an inertial frame for these purposes, it's going to be fixed above the table, and the vector r is constantly changing in this frame. But we can also imagine defining a reference frame placed on the table where it will rotate with the table. And we denote this new coordinate system with these primes on our x, y, and z. Okay. So before we get more into that demo, we'll go through a quick derivation of where the Coriolis effect comes from. So this is kind of the math-heavy part of the talk, but I hope that it helps some of you appreciate where this minus 2 omega cross r part comes from. So in our problem, we have our vector r, and in the inertial frame, its rate of change, i.e. the velocity of the point, is going to be equal to the tangential velocity omega cross r. And certainly if you've studied uniform circular motion, you've seen this definition of the tangential velocity. Now, if we can imagine that our rotating table is going around, maybe our rubber ducky wants to walk around on this table. Well, now the velocity of the rubber ducky in the inertial frame will be equal to the tangential velocity at the point of the table plus the velocity with respect to the rotating frame. So now we can write this a little more compactly with these I and R subscripts, which refer to inertial and rotating frame. To get to acceleration, we'll just take the derivatives of, with respect to time of both sides of that equation in the inertial frame. And in order to keep track of what's going on, I've labeled these 3 terms, 1, 2, and 3. The first term we'll simply rewrite as the acceleration in the inertial frame, because it's just the rate of change of the velocity, where the velocity is the inertial velocity in the inertial frame. And next we will expand the rate of change in the inertial frame of the velocity in the rotating frame, simply using the centripetal acceleration, which plus the rate of change of the velocity in the rotating frame. So this is sort of analogous to what we were doing back here with the vector r, and now we're just doing it with the vector vr. And so again, we rename our acceleration just to make things a little more compact. And then the third term is the messiest. We have to do the product rule, and then we can substitute back in this definition that we just found, and we get this. Okay, so that's just some algebra. And then we have our 3 terms. We can set those out, and we can set omega dot equal to 0, because once this table is going, and once the Earth is going, really, its angular velocity is not going to change by much, at least on the scale of weather forecasts. So we can get rid of that part, and we have our final equation for the acceleration in the inertial frame in terms of the acceleration of the rotating frame plus these extra terms. And so to put this in terms of forces, we just multiply everything by the mass of the object m, and then we scoot these 2 terms over to the left-hand side in order to get in terms of forces. And so we find an equation that we were looking for, which is that the force that is apparent is equal to the true force on the object minus these 2 terms, where the first term is called the Coriolis force term, and the second one is the centrifugal force term. So I maybe lost a few of you with that, so I'll do a quick demo that helps to illustrate how this effect happens in real life. Okay, so we're gonna take our vectors off the table and get this spinning. Actually, first, let's make the spinning. Woo, okay, so now you can all get a slightly better view of what's going on here. And to start off, I'll simply show how a moving object moves in a frame that's not moving. Okay, so I drop the ball into this tube, it's going to send it towards me, and wow, Newton's first law. Let's do that again. Okay, so everyone saw that. Okay, so now if we get our frame rotating a little bit, maybe a little faster, we can roll the ball again, and I promise you it'll go in a straight line. I'll show that again. So for this part of the demo, focus on just the path of the ball and try not to look at the lines on the page. Okay, so I'm gonna put this ball in when it's directly opposite me, and because it'll go in a straight line, it should move directly towards me, and it does that. But now if you focus on what's happening in the frame, in the grid that is on this inertial frame, we can see that it actually looks like a curve from their perspective. It came out here, and it ends up going here, right? So that's a curved path in that frame. And this follows directly from the Coriolis effect, because if we recall that the Coriolis effect, let's just write that up here again. Okay, so it's this term, right? It should be equal to the opposite of the angular velocity. So the angular velocity vector is coming out here. And we're going to cross that using the right-hand rule with the velocity vector that is coming out of the tube. So it should be in this direction. And that gives us that the opposite of the Coriolis of force is this way. And so the true Coriolis of force will be that way. So let's see, did we get that right? Okay, so it's rotating this way. Our velocity vector is going to be this way. It's rotating. No, sorry, I got that wrong. Okay, so the angular velocity vector is down in this case, which means that if we cross that with the velocity in this direction, oh gosh, then it'll be, okay, then it'll be that way, which is exactly what we see in the frame. It seems to curve left from the perspective of the rotating frame. Okay, so I hope that helps you get an idea of what the Coriolis force is and how it shows up in non-inertial frames. Okay, so then this brings us to how does this affect the Earth? Well, it turns out that these beautiful swirling patterns that you might have seen in a satellite image before of the Earth is caused by the Coriolis effect. And more specifically, the fact that storms rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere directly follows from the Coriolis effect. So to explain how that's the case, we can imagine that we have a low pressure system somewhere on the Earth, and like we explained earlier, we expect the wind to go towards that low pressure system. But the Coriolis effect is going to cause a deflection of that. And we can see what that effect will be using our wonderful globe here. So if we have, let's focus on the north to south wind. So if we have the wind vector that's going this direction, and the angular velocity is going this direction, then using the right-hand rule, which I'll get right this time, we can see that.
You're using your left hand, dude.
Oh my gosh. So, now I'm actually going to use my right hand. So we've got the angular velocity, we've got the velocity. So the opposite of the Coriolis force will be that way, and the Coriolis effect will be that way. Okay, let's see if I got it right. Hey, I did. It goes that way. So what we can see is this, it causes this deflection, which leads to, in the northern hemisphere, a rotation in the counterclockwise direction. And a similar thing happens in the southern hemisphere. I'm not going to go through that again, but you get the picture, which produces these swirling patterns. And the reason that you see them particularly well defined in hurricanes is because the pressure differential is much greater. These are really low pressure storms. And so as the velocity of the wind moves towards the low pressure, it's deflected, but then it's attracted more to the low pressure, and which means that the Coriolis effect becomes larger, which means that these really wrap up into tight, sort of circular-looking storms. So this brings us to the final section of my talk, which is on clouds and precipitation, and I'll be focusing mainly on cloud formation. Okay, so how do clouds form? What are the necessary conditions to produce clouds? And you might have an idea that this has something to do with humidity. And in particular, you might know that when the humidity is greater than or equal to, or when the relative humidity is greater than or equal to 100%, the air is saturated, and so that's when we might expect clouds to form. And what do we mean by relative humidity? Really, 100% relative humidity means only about 5% of the air has water vapor in it, or 5% of the mass of a chunk of air is water vapor. But really what it means is that if we have a puddle, say, out on the ground, the amount of water evaporating from that puddle and condensing into that puddle is equalizing, and so the puddle does not get smaller or larger. So this is the point at which those effects cancel out, and we have this equilibrium of water. And so to talk about our model of cloud formation, we can use this cartoon to illustrate the fact that water is cohesive and adhesive. So this comes out of the chemical fact that water is attracted to itself intermolecularly, and it's also attracted to a lot of other substances like glass, for example. And so that means it likes to stick to itself and it likes to stick to other things. But it turns out that the water-water cohesion, the cohesion between water molecules, is much stronger than between water and air. And this has an important effect that comes out in surface tension, which is that water droplets form surface area minimizing shapes. And you've seen this before, certainly on your window. When it rains, water droplets form, and they tend to bunch together in these somewhat circular shapes. That's because they're trying to minimize the surface area. And certainly if you've ever done this penny drop demo, which I did in middle school, and I feel like a lot of you might have done, you notice that pennies can hold a lot of water on them because the pennies wants to stick to itself really well. And this really comes out of the fact that, okay, so water is really well attracted to itself, which means that the forces will be all equalized in the middle of the droplet, but at the edge of the droplet, where it's exposed to the air, it's getting much more force and attraction to the water around it rather than to the surface. And so it tends to form a tension that it goes along the surface. And we can quantify what this means for the energy of a water droplet using the Gibbs free energy. And I'm not going to write out these equations explicitly, but we can think of the Gibbs free energy as being the energy that is the energy going in as work that is not pressure or temperature changing energy, which, because of the cohesive and adhesive properties of water, means that to create a volume or to expand a volume, negative work is required, i.e. energy is released, whereas to create a surface, positive energy is required. And because these two different functions, one, the volume goes with the opposite of r cubed, and for surface it goes with r squared, this has implications for droplets formation depending on their size. Well, it basically comes out of this fact that r squared grows faster than r cubed for small radii, and then it switches for larger radii. But this point of growth switches around, for water, around 150 million molecules, or 0.1 micrometers. Which means, when we add these terms together, that energy is released when a droplet grows, when it's larger than this critical value. But to grow a droplet from small requires an input of energy. And so the implication of this is that water droplets that are large grow larger, whereas water droplets that are small tend to grow smaller. And we can imagine this more intuitively in the idea that water droplets in small droplets on the surface have fewer neighbors to hold on to than the surface water in a large droplet. And this means that it's more likely to break off due to its thermal energy. So then how do water droplets form? If they can't grow when they're small, really small, from random collisions, then how do they grow at all? Well, what we're missing is aerosols in the atmosphere. And because of the adhesive properties of water, liking to condense onto surfaces like particulate matter, smoke, mold, pollen, dust, and other pollution, because water likes to collect onto that, we can use aerosols as sort of a starting point for a water droplet. And this, because aerosols are usually larger than 0.1 micrometers, then this allows us to grow water droplets. And indeed, this is how clouds do this. Because they've tested this in labs, and if you have perfectly clean air in a tank and increase the saturation past 100% humidity, you won't get clouds unless you have these particulate matter for the water droplets to condense on. Okay, so far we've talked about the basic ideas in weather prediction. We've discussed the physics that go into the equations of the atmosphere, and we've spent a little bit of time thinking about the Coriolis effect and how clouds work. Now, I hope that you can come away from this talk having a better idea of how fundamental ideas in physics are used to predict the weather and to turn this sort of complicated problem into one that's manageable and that computers can help to compute. And so with that, I'd like to acknowledge the people who have made this possible, in particular my advisors, Joel and Argendu, along with all the other physics and astronomy faculty, the physics staff, Trenny, Tom, and Bruce, who helped me with the demos and the technology for this talk, and also, in particular, Nyla, Daniel, and Andrew, who came to my practice talks to give me feedback and help me rehearse, and all of my other physics peers. And lastly, my supportive friends and family, and especially my girlfriend, Bex, who's been particularly supportive over the last couple of years. So I can take any questions you have now. Yeah?
So I have a question about one of the 5 equations.
Sure.
Do you remember? I think it was the one with temperature in it. It might have been the 4th or 5th one.
Okay.
So.
Okay. So not the momentum, not constant. Did I miss it? Was it the equation of state, or?
It was. Oh, it was the 4th one.
Okay, it was energy. Okay, let me see if I can find it.
Well,
Great.
I was just wondering. So, you have that derivative where you're following some element.
Yeah.
But then the temperature is typically defined, like, how do you define a temperature at a single point if you're following it?
Yeah, that's a really good question, right? It's hard to talk about what the temperature is of one molecule because it's sort of an average of many molecules, right? And so the way we get around that is we can sort of think of the air as being broken up into parcels or chunks of molecules, but that are still very small, so as to be treated infinitesimally. And so then we can find the average kinetic energy of this small chunk of particles to find the temperature. But we're still following the general flow because, right, water molecules in the atmosphere are going to be going generally in the same direction as the ones that are nearby, or the net flow from, yeah.
I have a question about clouds. You don't need to do this line. So you said that water would latch onto pollutants. So in the past 150 years, there have been a lot more pollutants in the air. Does that mean there are a lot more clouds since?
Yeah, that's a really good question. I think that pollution does affect cloud formation, and there have been some studies on how pollution during the week affects rain and when rain comes. I mean, you're not going to get more rain because of the pollution, but you might make it happen sooner rather than later because with greater particulate matter in the atmosphere, these clouds can form at a lower humidity level. Yeah.
if you enlarge your scale a little bit more and consider multiple planets, would you be able, based on these fundamental 5 rules, can you use the 5 for other planets to forecast or tell about the atmosphere of all those or the weather in them?
Yeah, you could use pretty much the same equations. Some of them are a little more complicated. For example, for some atmospheres, you can't use the ideal gas law because the fluid is really thick. The fluid is more compressed to the degree where the ideal gas law fails to work. But you can use these equations or some variation on them to predict the atmosphere in any planet.
So this might trigger another 60-minute talk.
Yeah.
You told us the constituent equations. How do they add up? What do you do to put it together?
Yeah, that's a good question. So I didn't really go into the numerical integration process, right? I assume is what you're talking about. Well, that's kind of a complicated system that I won't get into a lot. But we can use the idea of finite differences to just evolve the atmosphere over extremely small time steps, assuming that these changes are linear over extremely small time steps. And so if we use these equations to make small linear changes over an infinitesimal amount of time, then, or just a small difference time. Yeah. Yes?
How far in advance can equations like this look?
Yeah, that's a great question. Well, the fact of the atmosphere being chaotic means that we can't predict it through infinite time. And that time of predictability is probably around a week or 2. And so we can't really hope to have any decent forecast of precisely what's happening in the weather for any longer than about 2 weeks. After that, it's not much better than climatology. So, yeah.
Can I ask a slight follow-up question?
Yeah.
What are the factors that are introducing this chaos?
Yeah, well, it's the fact that these equations are nonlinear. Right? They're nonlinear, and if this was a math talk, I could prove it, but.
I have a question about specifically the use of weather satellites.
Mm-hmm.
Now, did weather satellites help because did it allow like a more frequent measurement than like points by using weather stations? Is that one of the main reasons why?
Well, probably that too, but probably the biggest part is the fact that you can get it for a lot of different points in space, right? Because this is a problem of finding good initial conditions for the atmosphere, right? You'll be able to predict the weather better the more you know about the current state of the atmosphere. And satellites really allow us to know things about the state of the atmosphere over places where maybe there are no people, like over the ocean, or in uninhabited places where we don't have weather stations. Yeah.
Did I follow up? So we need vertical
Yeah, we do.
resolution as well?
Yeah, totally. Because all of these equations are varying in 3 dimensions, we do need 3-dimensional information. We can sort of extrapolate what it is at higher altitudes from surface level observations, but that's also brings us to weather balloon launching, which allows you to get, at least for one point along the Earth, vertical profile of what's going on in the atmosphere. Yeah. Sorry, Sasha, go ahead.
So I'm curious what are the equations like solved on kind of like a grid or a lattice, and are they, in that case, for each point would you have to have like a weather station, or like are there some points where the data is kind of like interpolated, or?
Exactly, yeah. Yeah, there's a huge field called data assimilation where you try to take these sort of spotty observations and make a good estimate of what it's like in between. And that's exactly what the weather models are doing. They are on a grid of the Earth, which has varying resolutions depending on the type of model. And for a lot of those points, you don't have direct measurements, so you have to interpolate what it is. Yeah.
Based on your background and also your research, what do you think can be done moving in the future to make all these measurements more precise or add a factor to it to make this happen?
Yeah, that's a really good question. It's not really on the modeling side. I would say most of the advancement is going to be in observing the atmosphere better and in sort of just the inevitable increase of computing power, at least for a little while. Right? These models are being run on some of the most powerful computers in the world, and so as their computing speeds increase, we can increase the resolutions of the model and make them a little bit more complicated and a little bit more accurate. Yeah, Joel?
So I have a fun blue sky question for you. Say you're up at a geostationary satellite altitude with a highly instrumented satellite. How could you get height resolution?
Did you get height resolution? Well, I'm not sure, but I imagine you could do something with optical depth.
And what is optical depth depend?
Density of the atmosphere, good point. That's a really good point. So how close together the molecules are. And, yeah.
What could you do with
Do you do with different wavelengths? Well, I guess you could see how different wavelengths are absorbed or in the atmosphere, so that could certainly tell you about clouds and concentrations of different elements in the atmosphere. Yeah, Jeff?
Can you talk more about the effective gravitational field and how that?
Sure. Yes. That's so really, all the effective gravitational field is it's the real gravitational field on the Earth plus let's see, where is it? It's just and I didn't mention this, but you've seen it. Okay, I'm almost there. Great. Okay, it's just the centrifugal force. So because the centrifugal force is going to be pointing outwards, I guess always this direction, right? Because the Earth is. So the centrifugal force is going to point outwards, which is going to oppose gravity approximately. It'll oppose gravity exactly at the equator, and it'll oppose it to off angle near the poles. But basically, we include that in gravity just because it's easier to simplify things with that. Yeah.
I think we drilled this dude in. Well, we thank you.